Okay, so we're going to do two sections today, vector fields and then line integrals. And in the line integrals section, we're going to talk about a physical quantity called work. How many of you guys know what work is? A few of you from what, physics-ish? Physics. In fact, if you're in physics 155 right now, you probably just did that. Yeah, because I was sitting in on Moira's classes last week, and it seemed like that's where she was headed. So, yeah, so some of you that are doing that, you should get a lot out of some of the things that I'm going to talk about today. Okay, so the first thing we want to talk about is vector fields, and then we'll move on to line integrals, and then we'll use line integrals to compute work. And let's go to it. Let's see here. Let's look it up. Let's look up some vector fields here. And let's look up pictures of vector fields. Okay, so if you hover over any one of these images, what you tend to see is lots of little arrows pointing in sort of systematic ways. So here you see a bunch of arrows that appear to be kind of circulating around the origin here. Here are some arrows that are kind of radiating away from the origin, and lots of other examples. Here's a three-dimensional vector field. To sort of take advantage of the word field here and the fact that we live among fields out here in Walla Walla, you go out into the countryside and you look at a wheat field when the wheat's really tall, which you guys may not actually see very often here because you're not here when the wheat is really tall. But if you go out there, you've seen this in other places, you go out there when the wheat's really tall and the wind's blowing, right? And it pushes the wheat around. And the way that the wheat bends is an indication of how the air is behaving near those stands of wheat. And that's kind of what a vector field is, right? The stalk, wheat stalk is like a vector, and then the root down there is the point that you're interested in. And if I walk around the wheat field, or if I stand in a place and I watch the wheat blow around, when the stalk bends this way, I know that the wind is blowing that way, and when it bends that way, I know the wind's blowing the other way. And so I can sort of deduce what's going on with this invisible quantity, wind or air, by looking at its effect on the wheat field. And it's a very good example of a vector field. All those little stalks are vectors, and they're all out in a field. So what we want to do today is understand these vector fields, learn how to plot them a little bit, gain a little bit of intuition, and then move on and use them to compute work. So along those lines, let me switch over to notes, and I'm going to sketch a couple of very simple vector fields. This is not something that you want to do sort of routinely, sketch vector fields. It's very tedious, but I think it's worth doing once by hand, because you do gain some intuition about what a vector field actually is by doing it by hand. All right. No crashing. Okay. Let's go to the book, and I'm going to jump to, I'm going to try to jump to, why does this thing not want to behave? And it really doesn't want to behave. This laptop does not like this class. It does fine at 1 o'clock, but then that's just ridiculous. All right, keep it in this mode. Almost there. Although it may be partly due to the recording, because I don't record the 1 o'clock class. So I'll just write on it like this. So what I thought I would do to start out with is, at the end of this section, this first section, you're asked to plot some vector fields and then check your work with Sage's plot vector field function. David likes to use Sage in his classes. I don't use Sage, but I have provided you with a vector field plotter if you go to the class syllabus and you look at the supplementary column here. I don't know why I put it here, but the supplementary column here, the vector field plotter. We'll be using that today. And you can use that application to check your work for these problems. What I'd like to do is sketch these vector fields point by point so that we get an idea of what a vector field actually is. And I'm going to start with number 1, the vector field xy. So I'm interested in this vector field. And let's see how this actually works. So here's the x-axis, here's the y-axis. The way that a vector field works is you pick a point. Let's pick that point right there. The coordinates of that point are 1, 1. X equals 1, y equals 1. And what the vector field function, capital F, is telling us is attach a vector, attach the vector 1, 1 to that point. And what I mean is take the tail of that vector and attach it to that point. So I'll attach that vector, I'll take the tail of that vector and put it there, and the head goes up that way. So that's the vector 1, 1. And remember, vectors don't have position. They have magnitude and they have direction, but they don't have position. We're free to put them wherever we want. And when you're plotting vector fields, where you want to place them is you want to put their tails at the point. So at the point 1, 1, we place the vector 1, 1. And let's go around the horn here. At the point negative 1, 1, we want to attach the vector negative 1, 1. That's 1 unit in the negative x direction and 1 unit in the positive y direction. And you can imagine how this goes as I go around the block here. I get something like that. So there's 1, 1, negative 1, 1, negative 1, negative 1, and 1, negative 1. But those aren't the only points in the plane. In fact, every point in the plane has a little vector attached to it. Let's see what happens if we go a little bit further out. For example, let's go out to 3, 3 here. So what vector am I supposed to attach to 3, 3? 3, 3. And that means go +3, +3. And you can imagine, again, I can repeat this process all the way around. And I get something like that. And you might think, oh, this isn't so bad. And it's not. It's a little tedious, but it's not so bad. What about saying right here? What vector do I attach to that point? Zero, 3. Okay, so let's do something slightly more. How about that one right there? That's 3, 1. Sorry, that's 1, 3. That's 1, 3. What vector do I attach to that point? 1, 3. That means go over 1 and up 3. So it looks like that. And you can do this everywhere. What are some qualitative features of this thing? Bless you.
Go further out.
So yeah, vectors, the magnitude is the same as the distance to the origin. Good. Does everybody see that? Right. And how can you see that? Well, what's the magnitude of this vector? Square root of x squared plus y squared, which is not coincidentally, which coincidentally is the distance to the origin. So the magnitude of one of these vectors is precisely the same as the distance its tail is from the origin. Nick?
The closer you place
Right. And in fact, you can say even more about the direction. What can you say more generally about the directions qualitatively?
Points in the opposite direction from the origin.
These guys all point away from the origin. So a broader statement is that they all point away from the origin. Okay, let's look at us. Now that you have the idea of you're taking a point, you're attaching a vector to it, let's do something that's a little less trivial. I want to look at this vector field. This is, if you can get this one, then you've got it pretty well figured out. Let me draw oh, come on. Okay. So there's a coordinate axis. And let's be really careful about how this is going to work. So let's pick a point. Same point here. That's the point 1, 1, right? X equals 1, y equals 1. What vector do I attach to that point under this vector field? Negative 1, 1. So that vector. Does everybody see that? Okay, let's go around the horn. That's the point negative 1, 1. X is negative 1, y is 1. Negative 1, negative 1. Let's keep going. There's negative 1, negative 1. 1, negative 1. And finally, this guy, and you can probably guess, it looks like that. So this is slightly more interesting than the previous example. Let's pick a few more points here. How about this guy here? That's 0, 1, 2, 3, 4, 0, 4.
Could you clarify why point 1, 1 doesn't point 1 in the x direction?
Okay, so let's look at 1, 1. And we plug that into F. So X is 1 and Y is negative 1. Or sorry, Y is 1. So do you agree that that's the vector?
Yeah.
Okay. And then what this is saying, remember the coordinates now. This is the I direction, this is the J direction. So go 1 unit in the negative I direction,
Gotcha.
and 1 unit in the positive J direction. Okay, so now let's focus on this guy. That's the point 0, 4. F of 0, 4. Okay, X is 0 and Y is 4. So that means go 4 units in the negative I direction and 0 units in the J direction. So there's the vector that's attached to that point. And you can go around on this guy as well. Now remember, I'm just sketching arrows in at certain select points to try to visualize what's going on in the whole field. How would you describe this field qualitatively? In terms of magnitude and direction. Yeah, there's some sort of rotation, in a sense, around the origin. Counterclockwise rotation. Yep.
Direction 90 degrees.
So there's a sort of a counterclockwise rotation about the origin, and then we have the magnitude is proportional Okay. Now that I've labored through a couple of primitive field plots, let me move to the application and show you some more sophisticated field plots, and possibly, yeah, let's go here. Okay, so here's the first one we started out with. So the syntax is a little weird. Xi plus yj, you see how that works? I is the normal in the I direction, and j is the unit normal, or the unit vector in the y direction. Okay. That's the one that we just saw. If I put in, the negative thing is a little weird on this, I noticed. And let me turn this guy off. All right, so there's a much better rendering of that second vector field that I was trying to do. And you can see this rotational flow around the origin. Let me talk about -1 if you guys want to try to use this. For whatever reason, the guy that wrote this program, this just doesn't work. Negative, putting a minus sign in front of a variable doesn't work, so you have to sort of work a little bit harder at it. Okay, so just be warned about that, Chris.
Does changing the scale on the bottom just make it easier to visualize?
Yeah, so we can talk a little bit about that. When I was sketching over here, I was using a 1-to-1 scale. In other words, the coordinate distances that I was using were exactly the same as the vector distances that I was using. That's a 1-to-1 scale. In certain vector fields, that's problematic. So let me go back to the application and let me change this. The scale here is 0.1. Let me change it to 1. So this is what I'm doing by hand. And you can see what happens is the vectors start overlapping with each other and it gets really hard to see. And so the author of this program has enabled you to scale those vectors back just for the sake of visualization. So 0.1 seems to work fairly well for this guy, but you might want to tweak that thing depending on what your vector field is. There's no sort of hard and fast rule of thumb to tell you what that scale should be. Let me light up this other guy. So now both vector fields are on there at once. The red guy is x, y, and the yellow guy is negative y, x, the two fields that I started out with. What are some things that sort of pop out at you? They're perpendicular everywhere, right? So so what you can say is these two vector fields are perpendicular, and that's a much stronger statement than saying two vectors are perpendicular, right? These guys are perpendicular at every point at which they're defined, and it gives some really interesting geometric patterns here. What can you say about the magnitudes of these guys? They're the same, and so what we have are these nice little isosceles triangles everywhere, right triangles everywhere. Okay. Here, I want to do a different one. I'm going to turn this off.
If you like highlight the second one and pasted it into the, like an added to the first one, which you get like in between the two vectors. So you have like the right angles, which you get like a sum in the middle.
Yeah, I think you would. So we can do that if you'd like. So that would be x minus y here and y plus x here. So I don't think, you have to play around with these to get some real intuition, but that's essentially what's going on there. Okay. What I want to do now is talk about some of these, vector fields, yeah, they're pretty and all that sort of stuff, but how are they useful to you guys, especially you physics types and so forth. Let me put one in here that might be of interest to you. So there's that plus okay, and I think, yes, I need a J in there. Thank you very much. Okay. Let me crank up the scale on this to like 3. Okay. What, physics people, what does this evoke? Okay, I'll buy that. What else? Gravitational field. In fact, any kind of force field that's what? It's radially symmetric. This is an inverse square, right? An inverse square law. Gravity is an inverse square law, right? Meaning that the effect of gravity is proportional to 1 over the distance squared. So gravity weakens relatively quickly as you travel away from the Earth, for example. That's what's going on here. Which way? Let's pretend that this is the sun in the middle here. Let's pretend that's the sun. Gravity is always going to point towards the sun, right? And when you're near the sun, the force of gravity is quite large, and when you're far away from the sun, it's small. But it's always going to point inward. So this is a gravitational field. Or, sure, if you want to put like a proton right there, then you can talk about the electric field there, right? And it's the same thing. Electric field is also an inverse square field. So yeah, this is precisely where these things are useful. If you want, like I said, if you want, you can sketch some of these by hand, and then you can plug in some of these other ones just to see how they behave, like sine x, cosine y. Let's see what that looks like. Oops. I don't remember. So which one was it?
I think it's
Sine, cosine? Yeah, and we should probably shorten up the scale a little bit because we don't really have a good grip on. And maybe we'll crank it up a little bit. Okay. So that's a really weird vector field. It's not one that you're going to find in nature anywhere. Now I'll let you think about why that looks the way that it does. Let me go back to, yeah, let's do this guy here and get rid of this guy and knock this down to 1. Maybe 2. 1.5. Yeah, let's do that one. Okay. I'm going to save this to a PDF file here. And let's go into the next section. Let's put it on the desktop somewhere so I can find it. Here, save it. Okay, so before I leave this, I wanted to save that. I'm going to come back to that in a second. Let's talk a little bit about web work. I bring this up explicitly because this is something that's not discussed in section 1 of the text, but it's an important idea that I think is worth looking at right now with respect to vector fields. This is your first web work problem for tonight's homework, and you can read the problem there. Each of these vector fields is the gradient of a function, and these guys down here are the level curves of that same function. Now, do you remember what the relationship is between the gradient and level curves? perpendicular, right? The gradient at a point is perpendicular to the level curve through that point. Does that ring a bell? Good. So given that geometric information, can you match these guys up? Like, for example, the first one belongs to which set of level curves? C, exactly. Because these guys are all pointing away, and if you put a circle in here, that circle is going to be perpendicular to all of the vectors that it encounters. Right? Okay, let's move to the next one. So I see here's some A's and some B's. The A people convince me. Give me a specific example.
Well, if we're looking at, say, the vectors on the y-axis,
Yep.
yeah, they're pointing straight down, which is perpendicular.
Yeah, and that's the dead giveaway. On the other hand, if I look at those vectors along this axis here, they're probably, in fact, parallel. Right? In fact, I don't know if it's a coincidence or whatever, but in fact, this guy looks like it's parallel to this guy, which means something also, but it doesn't have anything to do with the gradient. Okay, so that was a geometric idea that I wanted to make sure everybody had in their head before they hit their web work tonight, because it's not in the book. So have fun with that. There's, I think, another problem exactly like it following. Let me double check here. Oh, I'm no longer logged in. Yeah, the next one is very similar, so I'll let you work with that. Okay, bye. Moving right along then. Let me go back. Where is that thing? Desktop. And let's look at this thing that I saved. Okay, I want you to imagine that you're a particle and you are in this swirl of wind, say. Gosh, this thing just really doesn't love me. Okay, and I want you to imagine sort of traveling around in this field. People that know about work from physics, what is it? Force times distance, right? Force times distance. So here's a little particle moving along in this force field. And what we would like to do is add up the work along that entire trajectory. So we're going to take a little piece of arc length, say right here, a little piece of arc length, that's distance, and we're going to multiply it by the force along that trajectory. And in that little region, we're going to get a little piece of work. And we're going to take all those little pieces of work all the way around the trajectory and add them up with, guess what? An integral. And we're going to get an integral that represents the work along this trajectory. Just so you know, again, I'm not a physics teacher, but I'll do the best I can here. Remember that work is positive if you move with the force field, and it's negative if you move against the force field. So, for example, in this stretch right here, I'm definitely moving more with the force field than I am against the force field. Agreed? And so you're going to have positive work there. How about in this little stretch right here? Negative? Because I'm moving, right? I started off, I don't even remember now. So I started off on positive here. And what about in here? Near zero, right? Why? Because I'm neither moving against it nor with it. I'm moving perpendicular to it. So these are the geometric ideas that we want to get into our heads as we explore this new idea. So if I'm moving with the force field, it's positive work. If I'm moving across the force field, there's no work. And if I'm moving against the force field, it's negative work. And we want to start summing these things up. That's where I'd like to end up by, say, 3:30 or so. But before I can do that, I have to sort of talk about how to integrate along paths. And that's where we're headed right now. So now we're in section 2. And we want to talk about line integrals. Okay. So the line integral, let me show you a picture from David's book here briefly. Oops, don't want to do that. There we go. Okay, the idea behind a line integral is you have some path in the xy plane. So the path is the bottom of this sheet. You have this path in the xy plane, and then you have a surface above it. So again, we're back to my sort of favorite thing to do, which is to walk around the xy plane and look at the surface above me. You have this path in the xy plane, and you have the surface above. And to start out with, what we'd like to be able to do is find the area of this sheet. Does everybody see how this sheet works? Right? It's the sheet that goes from the curve up to the surface. Can I find the area of that sheet? This is similar to, but not the same as just the integral from a to b f of x dx, right? The area under the curve. Except what's the big difference? In that situation, it's just flat, right? It's just flat. And here, we've got this thing that's bent. So that's the picture you should have in your head. Let's go back here and formalize it. So, So the line integral along C of f of xy is denoted this way. This is really for symbolic use only. This is not useful for computation. Okay, well, if it's not useful for computation, how the heck are we going to compute one of these things? Well, that's what I'd like to finish with. To compute is a couple of steps. You need a parameterization. You need to parameterize C. And then you need to substitute into this integral, and that's what I'd like to show you now. Okay. Let me try to sketch a picture for you. And let's get something like that. Our classic surface. And let's take a point down here, call it A, and another point over here, call it B, and some squiggly line from A to B. Okay. So there's the surface z equals f of xy. There's the curve C down below in the xy plane. And you can imagine that curve has an image up there on the surface. In fact, how do I figure out what that image is? How do I get from here to here? If I take this point and I plug it into F, I end up here, right? Does that make sense? Okay. Here's a little piece of DS. Let me change over to a different color. Here's a little piece of DS. And DS is arc length, little piece of arc length. And we can take that up to the surface. And what we get is a little narrow piece of the sheet. And guess what the area of that sheet is, that little narrow red piece of sheet? It's this guy right here. F times ds, right? F is the height, ds is the width of the base, and then the integral is going to add it up. So this is the area of the red piece. Okay, given all of this information, let's see if we can't turn this integral into something that we can actually compute. Okay, so we need a parameterization of C. Which I'm going to call R. I don't remember what David calls it in the book. And it's R, and T goes from A to B. So in the picture here, R of A is the point A, and R of little b is the point big B. And secretly A, right, A is not just one number. A is an ordered pair, right? It's got a position, XY position. And B is the same thing. It has an XY position. Is that clear to everybody? Okay, let's look at arc length. The arc length formula, think way back. Oops, can't use T. Let's use W. That should look mildly familiar. I'm not disappointed if it just doesn't pop right out of your head, but remember how this arc length thing works. You take little magnitudes of velocity and you add them up to get the displacement from A to T. I'm not so much interested in that guy as I am in the derivative of this guy. The derivative of the arc length formula is just this. And that comes from the fundamental theorem of calculus, right? If you want to differentiate a function that looks like this, you just take the integrand and you plug in t, and you're done. No work. And we can play a little bit of a game here, which, again, I'm not going to explain, but it does kind of justify what I'm about to do. I can separate those infinitesimals, ds on the left, dt on the right, and what I now have is a formula for ds. And I'm ready to finish this off now. The integral, the line integral of f ds along the curve C is the integral from A to B, f evaluated along the curve ds. And ds we just computed as the magnitude of r prime t dt. So let's break this out a little bit again, just so that you see what I'm talking about. I'll try to get both of these pictures on the same. This is the height of the little rectangle, right? Of the little red rectangle, f of r of t. and this is ds. So this is the area of one of those little red rectangles, and I'm going to sum up all of the rectangles from A to B. All right, let's see this in action. You really have to keep your wits about you when you're using this formula. So let's do an example. Let's evaluate this integral. Two plus x squared y ds, where c is, and I'll just draw c for you. C is going to be this guy. So C is the upper half of the unit circle, traversed counterclockwise from 1, 0 to negative 1, 0. This is a pretty straight up problem. This is something that you could see on an exam, for example. You have enough to now compute this integral. However, you can't just look at this thing and say, oh, 2s and then x squared ys, and then sort of plug in some strange numbers and get somewhere. There's nothing you can do with that thing, so just walk away. All right, there's nothing you can do with that notation except look at it and get the information out of it that it represents. First, we need a parameterization. What's a parameterization of this curve? Now we're going way back to the beginning of the semester. Can you give me a formula that will trace out this curve for a particular t range? Think sines and cosines. Sure. Over what range of t values? Does everybody agree with that? Okay, good. And it traverses it in the correct direction. Direction is important in this new area that we're learning. The direction of the contour matters. So we know that this traverses the upper half of the unit circle in the right direction, in the counterclockwise direction. What do we need in order to evaluate this thing? Well, we need to fill in all of the pieces from the formula above. So I guess first things first, we need to find r prime. Right? And then we need to find the magnitude of r prime, which is not terrible. In fact, it's about as nice as it gets. Sucks how the math professors always get all the easy problems. Okay. And then we need f of r of t. Okay, let's talk a little bit about how that works. What I mean by f of r of t is this guy's playing the role of x and this guy's playing the role of y. That makes sense, right? Because it's actually tracing out a curve in the xy plane. So f of r of t is 2 plus, what's x? Cosine t. X squared, cosine squared t. Y is sine t. So f of r of t becomes 2 plus cosine squared t sine t. Does everybody follow that substitution? Good. I'm now nearly there. I have all of the pieces in place. It's really just a matter of filling them in. The limits of integration are 0 to pi, f of r of t is 2 plus cosine squared t sine t dt. And what happened to the magnitude of r prime? It's just 1. And this is a Calc 1 integral that, you know, I would hope that you'd be able to pull off. Let's try it. 2t minus 1/3 cosine cubed t from 0 to pi. There's a u substitution there that I did in my head. Cosine squared t sine t. A nice u substitution here is u equals cosine t. And then you have a du out here, just waiting. All right, plug in pi and 0. Pi, what is that, -1 cubed? And 0. Okay, so if I did my arithmetic correctly, that turns into, let's see here. Is it 2/3? I don't know, good God. -1, that's a 1/3, that's a 1/3, 2/3, you're right. And that's the answer, whatever that means. Okay, so the area above that arc and below that surface is 2 pi plus 2/3. Again, not super enlightening. All right, let's move on now. So we know how to do, at least preliminarily, you guys will have to do some practice problems tonight and tomorrow, but preliminarily we know how to evaluate a line integral. Now we can move on and compute work. So a little piece of work along the curve C. Remember that work is force times distance. And that is not a cross product, it's just multiplication. Force times distance. What we're going to use for distance in this context is just ds, the little piece of arc length. Work over here is just, I'll call it dw. It's a tiny little piece of work, dw. And the thing I'm really interested in here is what's force? What goes in this box right here? And the answer is, it's the projection, it's the scalar projection of F onto R prime. Again, dredging up some old memories, scalar projection. If you don't remember the scalar projection formula, I'll give it to you. The scalar projection is F dot R prime over the magnitude of R prime. So the right thing to put into that box is the scalar projection of F onto the velocity vector. Let's do that. On the other hand, we just showed that ds is secretly this, and a lovely cancellation occurs. And so a little piece of work is really just, oops, I'm sorry, yes, that's right, okay, is really just that. And we use this so often that we have a slightly simpler notation. F dot dr, and dr is really just r prime dt. And the total work is just the line integral of this quantity. Okay? Okay, and what I'm going to do is finish in the next couple of minutes here with a calculation of work in a particular example. So that's the derivation. If you want, if that went by really quickly, I essentially just repeated what was in the book. Let's do an example from the book here. So I'd like to do problem 19 from section 16.2. Still circled from when I did it at 1 o'clock. Okay, don't be alarmed that this is 3 dimensions. I did that on purpose. Everything we've been doing so far has been in 2 dimensions, but in fact, you can add extra dimensions here, and the formulas sort of just add an extra coordinate, and everything works out. But I'll show you the example here, and then you'll see how it works out. So an object moves along the curve, this crazy curve, who knows what it looks like, for the parameter range 1 to 4. And while it's doing that, it's traveling through a force field that acts like this. And note here this shuffling of coordinates, y, z, x. I don't really have a good image of what the curve looks like. I don't have a good image of what the force field looks like. Don't really care. Okay? I'm just going to apply this formula here and figure out how much work is done. There are problems where it's really interesting to think about the geometry of the curve and the geometry of the force field. But at this point, what I'm interested in is getting you through the calculations. And we'll talk about the geometry next time. Okay, so we've got this curve. Trying to memorize it here. And we've got this force field, which is a really weird one. So at every point in space, what we do is we attach a vector of the form y, z, x. So if I'm sitting at the point x, y, z, I'm going to attach the vector y, z, x, whatever that means. And I'm going to travel along this little curve in 3 dimensions. Okay. To use this formula, I've got to calculate these quantities. Right here, I've got to calculate f and r prime. Okay, let's look at f. That's f of r of t. F of r of t. So here's r of t playing the role of x is this guy, y, and z. So everywhere I see an x, I use this. Everywhere I see a y, this. Everywhere a z, this. You can really get lost in these things. You have to stay organized. The first coordinate of f is y. Along the curve, y is t to the minus 1/2. The next coordinate is z. Along the curve, z is t. And finally, the last one is x, and along the curve, x is t to the 1/2. Does everybody follow that? What we also need is r prime. That's just good old calc 1, 1/2 t to the minus 1/2, negative 1/2 t to the minus 3/2, and 1. This integrand is just the dot product of those 2 quantities. So let's compute the dot product of these 2 vectors. And that's going to be a scalar quantity. That's 1/2 t to the minus 1 plus, it looks like a minus, actually. Minus, let me think about this, minus 1/2 t to the minus 1/2, it looks like. Stop me if I make an algebra mistake. And t to the 1/2. So there's the dot product. That gives me a scalar Now we're ready. Integral from 1 to 4, 1/2 t to the minus 1 minus 1/2 t to the minus 1/2 plus t to the 1/2 dt. That's just a Calc 2 integral, or a Calc 2 problem. That's 1/2 natural log of t minus t to the 1/2 plus 2/3 t to the 3/2. Everybody agree with that so far? Okay, now let's plug in 4 and 1 and subtract. Four to the 3/2 is 8. And then we're going to subtract off what we get by plugging in 1. Natural log of 1 is 0. So now we've got to simplify that a little bit. The natural log of 4 is 2 times the natural log of 2, which conveniently cancels with that 1/2. And let's see if we can't gather up some of the rest of this stuff. Negative 2 plus 1 is negative 1. And we've got a 16/3 minus a 2/3. And finally we have 11/3. And that is the right answer. I remember from doing it earlier, but just to prove it to you. Right there. Okay. So that's how you would do a work integral. Let me really quickly finish off with some other notations that you'll see in the book. Another notation that you'll see in the book you will often see this, the integral c f dot dr. Okay, we just talked about that. If f is some vector function f g h and r of t is x of t, y of t, z of t, then f dot dr looks like this, the integral from a to b, f g h dotted with x prime, y prime, z prime, dt. Now each of those primes is really dx dt, dy dt, dz dt, and then there's another t out there. If I do the dot product, all those dt's go away, and I get the new notation that you will often see. That looks like that. Don't be afraid if you see that. It's really just this. So if you see that, just go to this. And in fact, I should change the limits back as well. Back to C. So just write that string of equations down, and when you're working on your homework tonight, when you run into stuff like this, just back up a few steps and use this. Okay? Okay. Any questions? Yes, Lila?
So the star problem in section 16.1,
Uh-huh.
it just said to sketch the field. Is that all you really want us to do?
I don't know. Let me look at it here briefly. There's always something to say.
Like, are we just supposed to explain how you actually just sketch
I think it might be interesting. I'm just going to get my bearings here. Do you remember which problem it was? Number 5. So I think you can find something interesting to say beyond the sketch. So I guess that's what I'm looking for.
Okay.
All right.